Andrea Dio from the Vusek Group in Amsterdam, and today I'll be presenting copy on flip, hardening ECC memory against Rowhammer attacks. So before we get started with the meat of the presentation, a bit of a teaser slide. So Rowhammer to this day, even on modern memory modules, is still an unresolved issue. And we need to find some way to protect existing systems. So to this end, we present copy on flip, which relies on ECC to detect ongoing Rowhammer attacks. And we then use transparent page migration and offlining for vulnerable pages. And as I'll show later on in the presentation, we have a pretty low overhead with more than 95% attack surface reduction, and this includes kernel memory, which is also what sets us apart. So a bit of background first. The very first paper on Rowhammer was in 2014, and it showed that by accessing specific rows called aggressor rows in memory frequently enough, you would eventually end up with bit flips in victim rows. And after that, there has been a lot of media coverage on Rowhammer, so attacks on ECC, on basically showing that the problem extends also to non-adjacent rows, then over mobile, over the network, and more recently, attacks that show that the hardware mitigations put in place by the vendors are still vulnerable. And on the defensive side, there are three main classes of defenses which have been proposed. So refresh-centric mitigations are mostly implemented in hardware, and these aim to refresh the victim rows before a bit flip is injected. Then in software, there's often physical isolation-based schemes. So these aim to protect data rows by placing guard rows between either all data rows or specific security domains to absorb the potential bit flips. And activation throttling techniques. So these aim to limit the rate at which an attacker can activate certain rows in memory. And also a bit about ECC. So ECC is commonly implemented with the SecDead schemes. So you can correct a single bit error in a code word and detect two. And initially, ECC was thought to be kind of the perfect defense for Rowhammer, implemented in hardware, very efficient, and could correct single error bit flips. However, there are techniques to exploit even ECC-aware, or there are ways to exploit even ECC systems. And this is often done with one bit at a time templating in the very first phase of the attack. So templating is when an attacker tries to fingerprint memory and find vulnerable locations in memory where they can then use in later stages of the attack these bit flips for example, privilege escalation. And you need, because of the ECC function, and you need at least 3 bit flips in a single code word to evade the ECC function and exploit Rowhammer on these systems. So why do we need another software defense? It seems like between ECC and other software defenses and hardware defenses proposed, there doesn't seem to be much space for more types of defenses. The problem here is that most software defenses are impractical to deploy on a large scale, either because they incur in too much overhead or they make unrealistic assumptions such as the linearity of DRAM addressing, or they only protect certain hammering patterns. And whereas hardware defenses, there have been plenty of hardware defenses which have been proposed, and many of them are very interesting and they might end Rowhammer in the future. The problem is they're very slow to deploy. So because of how the production pipeline is set up by hardware vendors, these will take likely years to be deployed, and they will only be deployed on newer memory modules. So we really need to find some way to protect existing systems, and we need to do it as soon as possible. So today I'm presenting, as I said, copy on flip. And our target is systems which are equipped with ECC memory. So this is very common, for example, in cloud and server settings. And we do this by stopping ECC-aware Rowhammer at the very first stage of the attack, which is the templating phase. We have a fairly simple design, and we want to protect vulnerable memory at runtime. And by at runtime, I mean that we want to have negligible memory overhead when the system is not under attack. So here we have a diagram which kind of shows the high-level workflow of copy on flip. So we have ECC, which corrects the error transparently and then raises an interrupt usually, which the operating system handles. And that's where we come in. And what we do is we migrate the vulnerable page to a different location in memory, and then we also offline the old vulnerable page. So there are two main components to copy on flip, the first being the template detector, and this hooks into the operating system's error handling or error reporting subsystem. So on Linux, this is, for example, EDAC. And what we do is we only need one single bit to represent the state of a vulnerable page and whether it is vulnerable or not. We do this by adding a page flag in struct page. So this is the PG flip flag. And on the first bit flip, what we do is we set that page flag within the page, and we set that in order to monitor that page for further bit flips. And on the second bit flip, instead, we mark that page with the hardware poison flag. So that means we're going to eventually offline it in order to avoid memory reuse schemes. And the template detector then invokes the second component, which is the page protector. And again, it's a pretty simple design. So what we do is when we have our vulnerable page, we allocate a new page in a different location in physical memory. We copy over all the data and the metadata, update the relevant page table entries for that page, and then offline the old vulnerable page. Now, the problem is what is vulnerable memory? It's kind of hard to define vulnerable memory in software, at least, because Rowhammer is inherently a hardware failure mechanism. But if we want to defend in software from Rowhammer, we still have to have some operating system notion of what is vulnerable memory. So, of course, these are pages that an attacker can allocate themselves directly, and they can use these for templating. So these are user space pages, such as the ones that you can get with mmap or BRK system calls. But what we also look at is all the pages that the kernel allocates or the kernel can allocate on behalf of the attacker. So these are, for example, page table pages, which get allocated by the kernel as long as you keep allocating memory in user space. Or page cache pages that the operating systems, modern operating systems like Linux use aggressively to improve system performance. Then kernel data, which, for example, gets allocated for the duration of a system call, and kernel stacks. So the challenge here is that even though Linux already has some mechanisms to offline pages that have suffered from multiple errors throughout time, whenever an error hits a kernel page, they just ignore it and hope for the best. They hope to be lucky and that nothing bad happens with that. So what we have to do is, and what I'm going to walk you through now, is how we handle the migration for the different types of pages. So user space migration is, of course, the easiest case because most modern operating systems have support GNOME architectures, and with that comes the need to migrate pages around to have processor local memory. So we can just reuse that for user space pages. Then for page cache pages, we have to distinguish between two different types of page cache pages, either active or inactive pages. These are, so the active ones are mapped in some processes address space, somewhere in user space, so we can, again, reuse user space migration for that. If they're inactive, instead we have to evict them from the page cache and offline them. Now the tricky part comes with the kernel data, so I've mentioned vmalloc and slab. Those are the most commonly used allocators in Linux, at least, for kernel data. So for vmalloc, we actually implement page migration support for all the pages that back a vmalloc allocation. And what we do then is switch the backend for the slab allocator so that it no longer goes via the body allocator, which only gives you pages that are physically referenced and cannot be moved with vmalloc, so that we can actually move also slab pages. And finally, page table pages. These are the toughest ones. We can't redirect these pages via vmalloc because they reference each other at different levels of the page table hierarchy with the physical addressing. So what we do is we actually implement a reverse mapping within struct page in order to update manually the addresses to the new page we allocate. So some evaluation numbers, we actually evaluated the copy on flip with the hardware error injection and flip tables rather than just using Rowhammer. This was in order to have a more exploit agnostic kind of evaluation. And we see that more than 95% of the memory in the system is now movable on, with our kernel. And we aim to offer system-wide protection. So that's why we also include the kernel pages. And we also do no assumptions on a certain Rowhammer variant or pattern, except for the fact that it's a Rowhammer on ECC. So performance-wise, we also tested the copy and flip on with various types of benchmarking suites against a vanilla Linux kernel. And we see that for spec CPU, we get almost negligible overhead. This is to be expected because we don't necessarily modify user space allocations. On LMBench, which is a syscall-heavy benchmark, we redirected all the caches to go via vmalloc, and we still get a pretty low overhead of around 2%. And also, we managed to run Google Chrome on our kernel, and we ran the Mozilla Kraken benchmark with, again, like 1.1% overhead, which is pretty low. And what I want to stress is that we also have, as I said before, like no memory overhead when the system is not under attack. So to dig a bit deeper, though, into the overhead that copy and flip imposes to a system, we also tried to run a heavily saturated IO-intensive benchmark like Nginx. And there we see a bit more overhead, so it's like around 10% median throughput overhead. And we get that because of how Nginx basically forces the kernel to create and destroy slab caches continuously. So we have that extra page table walks that are involved with our slab caches. So in conclusion, modern systems are still very much vulnerable to Rowhammer. This includes the latest generation of DIMMs. And I presented the copy and flip, which is a simple design. And we also have an open source implementation for Linux. And I've shown that we have a relatively low overhead and a high attack surface reduction. So you can find many more details in the paper. You can scan the QR code or follow the links. And I'll take any questions now.
Derek Key, MIT Legal Laboratory.
Yeah.
Did you do any evaluation on on your system while a active Rowhammer attack was also present on the system?
Yeah. So I actually have a backup slide on that. I don't know if you can switch back to the slides. Unfortunately, I didn't think I had the time to go through it. That's why I didn't add this. So we actually tested for when the system is under attack with Nginx, because that was our most sensitive benchmark for performance overhead. And we see that actually, even if we use a maximum attack rate, so there's more detail about this in the paper, we only get around 2% overhead on top of normal copy on flip.
Thank you.
Cheers.
Hi, thanks for the great talk. Andrew Searles from UC Irvine. I was wondering if you had considered if a Rowhammer attack was done on the bit that you're using as a flag to note if the row has been changed or not.
That's a very good question, actually. I haven't considered exactly that. But I think, so the point is, as long as you have a single bit, ECC itself is going to correct that. So if you manage to flip the single bit in the page flag, ECC is actually going to take care of that.
Okay, thank you.
Cheers.
Hi there, great talk. So there's been some interesting recent work showing that Rowhammer also can have confidentiality implications. Do you have a sense, I think the answer is yes, that this would also protect against sort of that class of attacks?
Yeah, so it should, at the end of the day, Rowhammer, regardless of whether you use it to attack integrity or confidentiality, if we have some way of mitigating these bit flips, then I think it should be the case.
Thanks. Derek again. Going on my previous question, it seems like this system could also maybe be used to detect ongoing Rowhammer attacks itself, and be used as a to mitigate these ongoing attacks. Is that a possibility?
Yeah, so definitely. I mean, I think using ECC as a kind of like a Rowhammer performance counter is what we strive to do. So indeed, it's a pretty good way to detect ongoing Rowhammer attacks.
Yeah, I was thinking something along the lines of in your detection or on your copy on flip mechanism, if you could somehow track which pages are getting flipped and do some analysis to say, like, this same page keeps on getting attacked, and start analyzing what processes might be hitting the other rows of the memory. Maybe you can figure out that this process is doing something weird, we should shut it down.
So indeed, you could do that as well. The problem with that and basically reverse mapping row activations to processes is it's kind of hard to see what the correct DRAM address mapping is between physical addresses and a DRAM address. So you can have like best effort guesses, or I mean, there is a lot of work on reverse engineering that mapping exactly, and it does seem to work in most cases, but it's not as fine-grained to probably do a reverse mapping on that front.
Okay, thanks.
Okay, any other questions? No, I guess I have one quick question myself as well, right? So I don't know, actually maybe you have already shown it, but I might have seen it. Like, do you look into like the memory overhead of your mitigation solution?
Yeah, so I do look at memory overhead. So today I just spoke about memory overhead not under attack scenario. In the paper there's actually a full-blown analysis on various memory modules and how impacted they are and how much memory you would offline under attack scenarios. I think on the very worst memory module, it was around 10% of the memory which would get offline if you were to attack whole of physical memory.
And when you say offlining, would it be like free after that, or like maybe just like
No, so by offlining, we basically want to avoid an attacker from using memory reuse schemes to keep on attacking the system. So I think that there was a few papers also within the Rowhammer topic that used to do that quite a lot for memory massaging, and so we kind of render it unavailable to the allocator exactly for that